In this lesson, we are going to look at the Newton's second law of motion. Now, the Newton's second law of motion talks about the relationship between the acceleration, force, and mass. So we have three quantities. We have the mass, and the mass is just the total amount of matter present in an object. Then we also have the net force. So this is just the resultant force. Then also we are expecting to get an acceleration after the force is being applied toward an object. Now, what Newton's second law of motion states is that the acceleration of an object is directly proportional to net force and inversely proportional to mass. So now, what this relationship means is we can derive the formula from the given law. So here we have the acceleration where we can have so acceleration is equal to net force divided by the mass. So in symbols, we have A is equal to F net force over the mass. So we are going to look at the relationship between the acceleration and the net force. So the relationship, we say the acceleration is directly proportional to our net force. So what we are going to do is, let's say we have an object of 5 kg. Then the same object, so we have, let's say, a frictionless surface. So this object has the mass of 5 kg. Now what we are going to do is, here we apply a force of 10 newtons. Then the same object, now this time we are going to apply the force of 20 newtons. Okay, so now we can see that what we are trying to see is how much of acceleration will be produced from the first illustration here. So we want to see how much of acceleration will be produced here, and also how much of an acceleration will be produced. So what we are saying is we are assuming the mass to remain constant. So if we increase the force from 10 newtons to 20 newtons, what effect will this bring toward the acceleration? So let's now calculate the acceleration for the first part, which is part A here. So we can see that the acceleration is equal to net force, then divided by the mass. So for the net force, we are just going to use the 10 newtons since we are assuming that the surface is frictionless. So here, where there is the net force, we put 10 divided by the 5 kg. So we can see that 5 into 10 is 2 meters per second squared. So we can see that if we apply a force of 10 newtons towards an object with a mass of 5 kg on a frictionless surface, we are expecting to have an acceleration of 2 meters per second squared. So now let's also check now if we increase the force from 10 newtons to 20 newtons, so what happens to an acceleration? Okay, so acceleration is equal to the net force divided by the mass. So here we have the net force this time is 20 divided by the mass is constant, so 5 kg. So 5 into 20, we get 4 meters per second squared. So now we can see that the acceleration in the first part is 2 meters per second. Then the acceleration in the second part is 4 meters per second squared. So we can see that what happened is the first value in terms of the force on part A is 10 newtons. So what we did is we just doubled the force. So 10 multiplied by 2, it gave us 20 newtons. So we can also see that the first acceleration, which is acceleration of the first part here, we have 2 meters. Then the 2 meters per second squared also doubled. So thus we have this relationship of directly a proportion. So we are saying if we increase the force, we are expecting the acceleration also to increase. So the direct proportional kind of relationship tells us that when when one factor increases, the other factor decreases. Now let's also look at the relationship between acceleration and mass. So this one now we have a relationship where we have an inversely proportion. So what we are going to do is we are going to have two illustrations. Now this time we are just going to have two different two boxes having different masses, but we are going to assume we maintain the same force. So here let's say we apply the force of 10 newtons, then another object here we also apply the force of 10 newtons. So what we are saying is we are trying to make sure that the force remains the same, but we differentiate in terms of the mass. So let's say the first object here, object A, has a mass of 5 kg. Then the second object has a mass of let's just say 10 kg. So we want to see how much of acceleration will the first party produce and the acceleration that will be produced by the second part. So this time we are looking at the relationship between acceleration and mass. What happens to acceleration if we increase mass, or what happens to acceleration if we reduce mass? So let's find the acceleration for the first party. So acceleration is equal to net force divided by our mass. So our net force, we have 10 newtons over the mass is 5 kg. So we can see that here we are getting 2 meters per second squared. Then we can also find the acceleration for part B, where the acceleration is equal to the same formula, net force divided by mass. So the force remains 10 over the mass is 10 kg. So if we divide 10 into 10, we are expecting to have 1 meter per second squared. So let's now evaluate what has happened this time. So we assumed the force remained the same. So what happened was the first party, for the first part, part A, the mass was 5 kg. Then for part B, the mass was 10 kg. So we increased the mass, but let's look at the acceleration. So for the acceleration for the first part, when the mass was 5 kg, the acceleration gave us a 2. Then after we increased the mass from 5 kg to 10 kg, the acceleration reduced from 2 to 1. So we can see that here one factor is reducing. If we increase one factor, the other factor is decreasing. So that is the relationship we refer if we say inversely proportional. So this is what the second law of motion talks about in terms of the relationship between acceleration and force and mass and acceleration. Now let's look at how do we calculate the net force. So we are going to have some examples. Now we are whatever surfaces that I'm going to draw, we are assuming that these surfaces must be frictionless. So a frictionless surface is a surface that we are assuming to have no friction. and we know that the friction is just the force that opposes motion. So now, in a case where we have this as our object, then lying on a frictionless surface, then if we have the force of 10 newtons, if the question is find the net force, in a case like this one, the net force is just equal to the given force. So in our case, we can just say the net force is equal to 10 newtons. Now, let's look at part B. Okay, so what of the case where we have two arrows? The first arrow here, this arrow has 15 newtons. Then we have another arrow with 5 newtons. So we are going to look at the direction for each arrow, and we can see that these arrows are pointing in the same direction. So whenever we have the arrows that are pointing in the same direction, for you to find the net force, you need to find the sum of the two arrows or the two forces. So here we are going to have 15 newtons, then plus the 5 newtons, which is giving us a total of 20 newtons as our net force. So whenever you have 2, 3, or 4 arrows, as long as they are pointing in the same direction, for you to find the net force, you need to find the sum, or you need to add those forces or arrows that are pointing in the same direction. Now, what of an example like this one? So we have where this arrow showing that maybe a person is pulling an object, and this one has 10, 20 newtons. Then we have another arrow, then this one, let's just say 10 newtons. Okay, so regardless of the position of an arrow, as long as the two arrows are pointing in the same direction, the net force must be found by adding the two given forces. So we are going to say 10 newtons plus 20 newtons, which is giving us the value of 30 newtons. Okay, let's say now if this time we have, now let's say we have two arrows pointing in different directions. So if this arrow has the value of 12 newtons, and also this value has the value of 12 newtons. So what happens if we have two forces acting in opposite direction, and those two forces have the same magnitude? So in this case, we are going to find the net force by subtracting. So whenever we have two or more arrows, as long as they are pointing in different directions, we are expecting the value. For us to find the value, we need to subtract. So here we are going to have 12 newtons minus 12 newtons. So we can see that here we are going to have 0. Nothing will happen because the two forces will cancel each. Okay, now let's say if we have two arrows pointing in different directions, now having different magnitudes. Let's say this one has this one is pulling with a force of 50 newtons, and the other one also is pulling with a force of 30 newtons. So we can see that the one force is greater than the other force. So for this one, our net force will be found by subtracting our 30 newtons from the 50 newtons, which is our net force should be 20 newtons. So at least now we have a picture on how we can find the net force. So in summary, we are saying if you have arrows pointing in the same direction, you add. If you have arrows pointing in different direction, you need to subtract for you to find the net force. Now let's have the example that involves now the mass, the acceleration, and the net force. Okay, so now the first example, we have a car, and this car, we can see that we have two forces. One force has a value of 1600 newtons, and the other force has a value of 400 newtons. So we can see that this greater force with the value of 1600, we can see that this force was the one produced by the engine. Then this force with the value of 400 newtons, this should be the friction force, and the mass is 1000 kg. So now the formula for acceleration, we say that acceleration is equal to net force divided by the mass. So we can see that first we need to find the net force, and we said net force can be found by adding or subtracting the two given forces. So in our case, we can see that we have two arrows pointing in different direction. So here, what we are going to do is we are going to begin with the force produced by the engine. So for this car to move, the force produced by the engine must be greater than the force produced by the friction. Then plus the friction force. Now, don't worry about the sign, the positive sign, the adding. We need to know that as long as you have the friction force always opposes the movement of an object. So therefore, the friction force will have a negative value. So the engine force in our case is 1600 newtons, then plus the friction force 400. This one will have a negative 400 since it is going in the opposite direction. So we have a 1600 newtons. Then we know that if we multiply this positive and the negative, we are going to have a minus. Then we have 400 newtons. So if we subtract a 1600 minus a 400, we get a 1200 newtons. Or if you want, you can just go direct. As long as the two forces or arrows are pointing in opposite directions, we just found the net force by subtracting the two forces. Now, since now we have the net force, we can go back to our formula. So acceleration is equal to the net force is 1200 newtons divided by our mass is 1000 kg. Now, the other thing that you need to take note of is make sure as you are calculating the acceleration, the mass should always be in kilograms. So sometimes you may be given mass in grams, so don't forget to convert it into kg. So now if we divide 1000 into 1200, we are getting about 1.2 meters per second squared. So this was the acceleration of the car when a net force of 200 was applied to an object or a car of mass 1000 kilograms. So let's have another example. So example 2, calculate the net force required to give a 3000 kg box an acceleration of 2.5 meters per second squared. So we have this surface, which is a frictionless. Then we have a box here. Now this box has a mass of 3000 kg. Then we are also given the acceleration. We are told this box, when that force was applied, this box had an acceleration of 2.5 meters per second squared. So now the question is, we want to see how much of force was applied for acceleration of 2.5 meters per second squared to be produced. So here we are looking for force. So we said for us to find the net force is equal to mass multiplied by the acceleration. So from the given data, the mass is 3000 kg multiplied by the acceleration, which is 2.5 meters per second squared. So if you type this in your calculator, so we have 3000 times 2.5. So if you can just move 1 0, we have 300. 300 times 25, so we can just say 25 times 3, that is 775 plus the 2 zeros. So we are expecting to have a resultant, our net force of 7,500 newtons. So this is how we can answer a question like this one. Okay, let's see another example. Okay, so now we can have the last example. The figure shows the forces that act on a car of mass 1,400 kg. The mass includes the mass of the driver. Okay, so now we have a car here, and we have two forces. There is a 3,800 newtons. This force came from the brakes that were applied, and also there is also another force of 400. This one is a friction. Now the friction force and the force from the brakes opposes the movement or overcomes the force produced by the engine. So we can just add from the diagram. There was a certain force that was applied by the engine. Now for this car to stop, the force applied by the engine must be greater than the sum of the force of the brakes and the friction force. So here we are not going to look at the force produced by the engine. So let's just look at the two forces that are opposing the force produced by the engine. Now, whenever you have the force produced by the brakes and the force produced by the friction force, these two forces must be added. Now, they need to have a negative sign because they are pointing in an opposite direction compared to that of an engine. For us to find the first question, which is question A, we are trying to find the net force. So here, the net force for the first part, the two forces, we have negative 3,800 newtons minus another force of 400 newtons. So the reason why these two forces have a negative sign, it is because they are pointing in an opposite direction compared to the engine, or they are moving toward the negative x-axis. So the friction and the force produced by the brakes must always have the negative signs. And we know that whenever we have the negative signs, we are going to add and maintain the signs. So 3,800 plus 400 newtons, we have the total of 4,200 newtons. So this is our net force and our net force for the first part. So the negative, it is just showing the direction, or it is just indicating that we are looking at the force that is against the engine force. Now for question B, acceleration of the car. So acceleration, we said acceleration is equal to net force divided by the mass. Now from the question, we are told that this car stopped. For question C, we can see that let's look at question C. We just get some data from there, how long it takes the car to stop. So since it takes, we are looking at the deceleration, so the value of acceleration must be negative. So we can see that from the given data, our net force is negative 4,200 newtons divided by our mass. We can see that here our mass is 1,400 kg. So here we are going to get an acceleration of 3 meters per second squared. So this is an acceleration when a car is slowing down until it comes to a stop. So this is our acceleration for part B. Then for part C, how long it takes the car to stop. So from the time the force from the brakes were applied up to the time where the car stops. So we're trying to find like how long. So time, we are interested in time. So we want to find how many seconds were taken for a car after the brakes were applied until the car stops. And we have been given the initial velocity. So what we are going to do is, let's look at the data. Let's see what we have from the data. So displacement, we don't have the displacement. The initial, we have been given, if its initial speed is 15 meters per second. Then the final velocity is 0. So whenever you have been given a condition when an object or a car comes to a stop, the final velocity is always 0. Then we have the acceleration is -3 meters per second squared. Then our t we do not have, so we are trying to find the time taken. So here we are going to use one of the equation of motion. So the equation that we are going to use is final velocity is equal to initial velocity plus acceleration times z times so plus at. The reason is we have the final velocity 0, the initial velocity we have it is 15 meters per second, plus the acceleration is given -3. Then we are solving for t, so we can say 0 here, we have 15. Then we can multiply positive by negative, it's -3 times t, that is 3t. So we are going to move our 15 to the other side. So if this 15 moves to the left side of our equation, we are going to get -15 is equal to -3t. So in order to find the value of t, we are going to divide by -3, even this side by -3. So our final answer, time is equal to, we can see that the two negatives cancels, 3 into 15 is 5 seconds. So this is the time that the car took from the time the brakes were applied until it came to a stop. So that is the main idea behind the Newton's second law of motion. So that's it for this video. If you enjoy the video, please press the like button, subscribe and share. Thanks for watching.